Hi! As we have seen, the gradient vector is a useful tool in computing directional derivatives. But what exactly does the gradient vector mean? What is its interpretation in terms of slope and rate of change? We will investigate these questions in this lesson. In particular, we will find that the gradient indicates the direction of so-called steepest ascent. The conclusions we will make during this lesson are all based on the formula you can see on the slide. It states that the directional derivative in the direction of the unit vector u is equal to the length of the gradient vector times the cosine of the angle theta between the vector u and the gradient vector. Indeed, this follows from the fact that the directional derivative is equal to the dot product of the gradient vector and u, since the length of u is equal to 1. In particular, it means that if we consider the directional derivative in a particular point, then we can view it as a function of the angle theta. Let me show what I mean using the applet you'll have access to during this lesson. Here you see the graph of the function x squared plus 3y squared times e to the power minus x squared minus y squared. Down here you see a contour plot with the point P indicated at which we consider the directional derivative. The green plane is the vertical plane in the direction of the vector u in which we take the directional derivative. And down here you can see the intersection of the green plane and the graph. In other words, the slope of this graph is the directional derivative in the direction u. Up here, I can vary the angle theta between the vector u and the gradient vector, which points parallel to the positive x-axis in this point P. Changing theta, of course, means changing u, as you can see, since the green plane rotates as I change theta. That also means that the directional derivative will change as I change theta. Down here, you can see a graph of the directional derivative as a function of theta. As expected, it looks simply like a cosine. The pink dot indicates the value of the directional derivative at the current value of theta. Notice how it moves as I change theta. It has a maximum when theta is equal to 0 and a minimum when theta is equal to pi. Finally, we can also see that it is equal to 0 when theta is equal to pi over 2. Let's put in clear terms what this all means. So, the directional derivative is largest when the vector u has angle 0 with the gradient. In other words, the direction of the gradient itself is the direction with the largest directional derivative. Thus, the direction of the gradient is the direction of steepest ascent. Moreover, the value of the directional derivative in this direction of steepest ascent is the length of the gradient. Similarly, the directional derivative is lowest in the opposite direction of the gradient. In other words, in the direction of minus the gradient. Thus, the direction of minus the gradient is the direction of steepest descent. Again, we see that in this direction, the value of the directional derivative is simply minus the length of the gradient. Consider the following example. Here we see a function, but at several points it is not clear at a glance what direction would be the direction of steepest descent or ascent. Perhaps we are interested in these directions in the context of some optimization problem. In particular, we might like to move in the direction of steepest ascent. But for that we must first know what that direction is. To determine it, we first compute the partial derivatives of our function so that we may proceed to compute the gradient vector. In particular, at the point 3 over 2, 1 over 2, we find that the direction of steepest ascent follows the vector 8 over 9 pi squared, 8 over 3 pi squared. And the direction of steepest descent follows the vector minus 8 over 9 pi squared, minus 8 over 3 pi squared. If we have a look at the equation which led to this analysis one more time, we may note that there is one more particular value for theta that we may consider. Namely, what happens when theta is equal to pi over 2 or 3 pi over 2? In other words, what happens in the direction perpendicular to the gradient vector? Indeed, we can readily see that the directional derivative in this direction must be 0, since the cosine is also 0. Since the directional derivative provides the slope in the given direction, this means that the slope in the direction perpendicular to the gradient must be equal to 0. In other words, the function does not change in this direction. Returning to the example from before, we see indeed that when the angle theta is at pi over 2, the gradient vector is perpendicular to the level curve of the function. Indeed, level curves are exactly the curves along which the function remains constant, and thus the directional derivative is 0. Formulated as a theorem, we can see that the gradient vector is perpendicular to the level curve at the point AB, which means that the gradient vector is perpendicular to the tangent line to the level curve at the point AB. Turning this reasoning the other way around, we see immediately that the gradient provides a quick way to find the equation for the tangent line to any level curve. As you can see on the slide, the equation at the point AB simply has coefficients given by the relevant partial derivatives, and the right-hand side such that the point AB is on the tangent line. Consider the following implicitly defined curve as an example. Since we can see it as the level curve at level 0 of the indicated function capital F, we can quickly find the equation for the tangent line at any point by computing the gradient vector of f at that point. Indeed, here you see the computed gradient of capital F. And by plugging in the values at the point, we find the actual equation for the tangent line at that point. This same reasoning will work equally well when considering a function of 3 variables. Indeed, the gradient vector must be perpendicular to the level surfaces of such a function. Suppose, for instance, we want to find the equation for the tangent line to the ellipsoid given by the equation on the slide. Again, we can see that the ellipsoid has a level surface for the function capital F on the slide at level 3. Again, by finding the gradient vector and plugging in values for the point, we easily find the equation for the tangent plane to the ellipsoid at that point. For instance, if we consider the points 1 over 4 square root of 6, 1 over 8 square root of 6, 1 over 4 square root of 2, then we find the equation for the tangent plane indicated on the slide. Now we might continue generalizing to 4, 5 or 6 variables, but hopefully you are able to generalize the concepts of this lecture to those situations without my help. In particular, I hope you have been convinced that the gradient vector is a convenient but also a meaningful concept. In any case, make sure to practice using the exercises below.